Good morning, physical science class. Today we want to have a lesson from 9C about something called specific heat. Have you ever noticed that in the springtime, sometimes there'll be a day where it's really warm out? It might be 50, 60 degrees after a long winter of it being cold. And you'll pass by a pond. You go, that pond's still covered in ice. There's still a lot of ice in that pond, even though it's so warm out. That is because of something called specific heat. Another example of this is sometimes you leave something metal out in the sun on the pavement and you go to pick it up and it seemed really, really hot to the touch. Again, that's because of a concept called specific heat. Specific heat is the amount of thermal energy that must be gained or lost in order to change the temperature of a substance. And so when we look at different particles have different specific heats. When you begin to look at things like metals like silver, copper, gold, aluminum, lead, they have relatively low specific heats compared to water. Water has a very, very high specific heat. That means that it takes a lot of energy in order to change the temperature of water compared to other substances. Some of the some of the features that things that make that really, really important to our world is it keeps our our climate stable on this planet. Without the high specific heat of water, our temperature would fluctuate extremely during the day. As a matter of fact, some of the most arid places on this planet, that means places that are very, very dry, like deserts, experience extreme changes in temperature, especially between the night and the day, depending upon sunlight. A desert will actually be very, very hot during the day, but relatively cold at night because the temperature will go so high during the day and come back down so low during the night. And the reason that is because of the lack of moisture in the atmosphere because it's very dry and that wet the water in the atmosphere water keeps the temperature stable. Also, another thing for us to take into consideration is it takes a lot of energy to change phases, to change from a solid to a liquid and from a liquid to a gas. It takes a lot of energy to do that. Two of the terms that we're going to learn about is latent heat of vaporization, the amount of energy it takes to change from a liquid to a gas. I know it says here water. That's probably should be changed from a liquid to a gas, but you get the concept. And latent heat of fusion is the amount of energy it takes to change from a solid to a liquid. Now these values here, 2,256 joules per gram and 333 joules per gram, are for water. They're for water. Okay? It's going to have a different heat of vaporization and heat of fusion for a different element like gold, silver, copper, even hydrogen, oxygen. They all have a different heat of vaporization and heat of fusion. But the structure of a water molecule makes it very, very stable. It makes it hard for it to change temperature. So now we want to apply our knowledge about specific heat to a couple of specific word problems. When it comes to your homework on thermodynamics 9C, questions 10 and 11 are word problems about change in state and how much energy it takes to change the state of something. You can take these problems, these next three problems that I'm going to work on, and you can apply these to your homework. You can work them out on a test. There should be no excuse for you to be able to get these wrong because I'm just simply taking what the book's giving you, what the test is giving you, and I'm reproducing these questions. They're not exactly the same, but you should be able to get the answer here. So first of all, it says, how much energy does it take to raise the temperature of 22 grams of water 11 degrees Celsius to 29 degrees Celsius? So let's picture that we have a glass of water. And in this glass of water, we have 22 grams of water. There's a lot of, this is much more than, this is a small glass, all right? But what we have here is we have 22 grams. And originally we take the temperature of this glass of water, we find it to be 11 degrees Celsius. During the day, we leave it out in the sun. And as we leave it out in the sun, the temperature begins to increase. And at the end of the day, we come back and we find that the temperature has increased to 29 degrees Celsius. What is the change in temperature that has occurred? Well, the final temperature minus the original temperature, I use 0 for like at the beginning, is going to tell us the change in temperature that we had. So we ended with 29, but we started with 11. What is the difference in temperature that we had? Well, if you said 18 degrees, you'd be right. Now, what we want to do is we want to find out how much energy the sun provided in order to change the temperature of that water. So first thing we're going to do is we're going to start with the specific heat of water. 2 slides ago, we had a formula unit that is going to be very, very important for us to be able to solve this problem. It said that there are 4.186 joules. It takes 4.186 joules to raise the temperature of 1 degree Celsius of 1 gram of water. So it's joules per, and usually when I'm doing a problem like this, I usually write it, and I'll probably say it this way, so I usually write it grams per degree Celsius. So that's what we're going to do. Now, there's a concept that I've kind of done a few times with you this year called unit analysis. And what we want to do is we want to kind of make this chart that's going to help us to solve this problem. The first thing that I notice is that there are 22 grams of water that was given to us in the problem. Over here, there's 22 grams of water. That allows us to cancel out the grams. Now I only have the units of joules and Celsius, but energy is calculated in joules. So the other thing that I want to do is I want to put the total change in degrees Celsius. Well, we changed it 18 degrees Celsius. That will allow us to cancel out the degrees Celsius. So I just do multiply across the top and I leave the unit that's given. So I do 4.186 times 22 times 18. And I got a grand total of 1,657.656 joules. Joules is my unit. Now I want to finish the problem by putting in proper significant digits. You will see that there are 2 significant digits in the question. So using the multiplication rule of significant digits, I'm going to say that there are 1.7 times 10 to the third joules. If you wanted to put 1,700 joules, I would find that to be acceptable too. Pretty simple question. I think you're all very, very capable of doing that. Another one, another question, it says we have an ice cube. So let's provide ourselves first with a free body diagram. Let's just give ourselves an ice cube. And it says we want to melt that ice cube. It takes quite a bit of energy in order to melt an ice cube. Actually, we're going to talk about this more on the next slide. It takes a lot more energy in order to boil water than it does to melt an ice cube. You've probably experienced this before. Have you ever tried to boil water, or have you ever tried to keep an ice cube from melting? It takes a whole lot less work to melt an ice cube than it does to boil water. So it says here that we have, excuse me, an ice cube that is 34 grams. And we want to turn that into a puddle. So how much energy does it take to go from a phase change from that ice cube to the puddle? So that's the question we're working on here, is from a solid to a liquid. Now, something very, very important for you to understand is that there is no change in temperature going on here. Just we say it's already at 0 degrees Celsius, the fiducial point of water in Celsius, and it's just going to melt. Okay? So we're going to start with our formula unit. It says right there, there's 333 joules per gram, and this works for water only. This doesn't apply to another element. Like if I had a block of silver, it takes a different amount of energy to turn silver from a solid to a liquid. It also occurs at a much higher temperature than 0 degrees Celsius. And this one's actually kind of a little bit easier because you can notice that for the latent heat of fusion, there's no change in temperature, so my units are only joules and grams. States that right there, 333 joules per gram. So that means if I want the amount of joules, the only thing I have to get rid of is the grams. Well, the question says that there's 34 grams. So I cancel out the grams, and then I just do 333 times 34, and I'll get 11,322 joules. I go back to, and right here, I know it says 0, and you might think that that's something that we should pay attention to in the final product here, but I'm going to ignore that for this question and this question only, because that's just a baseline of a fiducial point. So when it comes down to what the energy is, we're going to say that it takes 11,000 joules to melt the ice, or 1.1 times 10 to the 4th power joules. Either scientific notation or the standard answer is applicable. All right. Got one more question for you. In this one, it says, how much energy does it take to vaporize an ice cube? So just like last time, we're going to start out with an ice cube, and then we're going to go to our puddle, the liquid. So we go from a solid to a liquid, and then from a liquid to a gas. Now, there's something that we need to take into consideration here, and this is something that we'll talk about in physics class. There's actually a different specific heat for ice and a different specific heat for steam than there is for water. Once you get into a different phase, there's different rules that apply. It actually takes a little bit less energy to change the temperature of an ice cube and steam than it does the liquid water. But for 9th grade science class, we're going to stick to 4.186 joules per kilogram, or per, excuse me, went back to physics class for a second, per gram, excuse me, per gram degrees Celsius as the specific heat of water. And so how how many grams do we have in this particular question? Well, it says in the problem, it says we have 115 grams. So we can put up here 115 grams. And how many degrees does it change? If it starts at -9, and it goes to 0, and then from 0 it goes to 100, and that's where it boils, and then it goes up to 109. So what is the total change? Well, what if we did that same thing we did 2 slides ago, where we find the difference of the two? So we'll take our temperature final minus our temperature initial. So temperature final minus the temperature initial to get the change in degrees Celsius. That's 109, not 119. So we have 118 total degrees that we have changed in degrees Celsius. So we changed a total of 118 degrees Celsius. Degrees Celsius cancels, grams cancel. The only thing left is joules. So we'll multiply across the top. 4.186 times 115 times 118 gives me a grand total of 56,804 joules. Now, I want to change from ice to water. And in order to change from ice to water, a few slides ago, we learned that that's dependent upon the latent heat of fusion. And according to even the directions here, it says that there are 333 joules per gram to melt the ice. And we had 115 grams of ice. Grams cancel. The only thing left is joules. So we'll do 333 times 115 to get 38,295 joules. This is to change the temperature from -9 to 109, which seems like quite a variation in degree temperature. This is the amount of energy simply to melt. And now we want to do something called the heat of vaporization. That's to change from water into steam. Water into steam. It says that there are 2,256 joules per gram. And there are 115 grams of water that we're changing into steam. The grams cancel, and 2,256 times 115 gives me, I don't know why it keeps bouncing back and forth, gives me 259,440 joules just to boil. Have you ever heard the phrase, a watched pot never boils? There is a scientific explanation to that. So if you take a pot of water and you raise the temperature of that water, the water is actually going to change pretty quick on how fast it will get up to temperature where it can begin to boil. But it takes a lot, substantially more energy in order to boil that water. So we're going to take 259,440, and if we want to find the total energy, we're going to add up the boiling, the melting, the temperature change. So we'll take 259,440 plus 38,295 plus 56,804 equals a grand total of 354,539 joules in order to take this ice cube at -9 degrees and turn it into steam at 109 degrees. And if we applied the one significant digit, it takes roughly 400,000 joules. I got one significant digit from right there in the question. So approximately 400,000 joules to change that water. Just so you kind of know, one of the things that is very, very important, like as you age and as you begin thinking about concepts that you need to know, one of the things that they would like you to be able to do is to take the concept of change of state and to turn it into a graph about the change in degrees Celsius and the amount of energy that it takes in order to change it. So it goes up at a constant rate until it hits 0 degrees, where it will begin to melt. So the temperature changes. Maybe it starts at -9, like in this question, and it goes up, 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 up until it hits 0, and then it kind of flattens the amount of energy used as it melts, and then it begins to climb again. It goes up, 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 until it gets to the next fiducial point of 100 degrees, where it begins to boil. And it actually goes flatlines for longer time while it boils, and then it begins to climb again. So this is a graph that illustrates what's happening as water changes temperature. Thank you guys so much for paying attention. You can use this video, these slides. I will also make sure that there's an inked version of the slides in your notes, and you can take this and you can apply this to your homework. Have a great day.